screen.
HDMI1.
There we go. Perfect. All right, so you can hear me. That's good enough. I'll share screen. All right, 208. All right, everyone ready? All right, so welcome everyone to my second talk in Physics 712. The second talk will be going over my current research, and I've given it the name FoRest. So let's get into it. So FoRest comes from initially, I myself, as a new scientist on this project, and you as viewers of this presentation, I want us to first kind of break down this sentence: a conceptual design for a new FoRest of scintillating tubes for reactor neutrino direction finding. I know that's a jumble of words right now, but by the end of the talk, I hope that you guys have an understanding of the work that's gone into this project so far to create that sentence have meaning, and what that physically means, what I'm doing in 109 Watanabe every single week, and ordering parts to design and build. And hopefully by the end of this presentation, there's a clear understanding of why this is an interesting scientific endeavor and what could potentially be occurring in Ohio for a new reactor design. So this project is a conglomeration, or specifically this sentence, comes from research between John, Mark Duvall, and myself. John Learned being senior faculty here at UH, Mark Duvall being a recent postdoc who I believe got his doctorate from UH last year in summer. And this is one of 3 papers. So very quickly what happened was I had joined John's group to help build a scintillator, since I had experimental experience with radiation detection. And Mark was turning his PhD into a publication. And I have a double degree with liberal arts with political science, and so I enjoy writing a little bit more than the normal physicist. And so, like any good newbie on a group, I offered to do the most miserable work, and John and Mark were all too happy to let me do all the references that were missing in the LaTeX file. And because of that and hard coding some graphs, they ended up putting me as an author on this paper, which is really, really cool. Obviously this is Mark's PhD, which I was not here for, so I felt it was a little undeserved, but they said I had certainly put in enough. So that was great. So fast forward to this winter break, a couple of months ago, and we submit this directionality paper, as it was called, to our affiliates at Lawrence Livermore Labs. They take one look at it and go, this is 3 papers, 3 publications, easy. And so now we've broken it up into 3 papers. The first being a theoretical overview, a second being conceptual designs with the simulations, and the final paper being the actual design as a result from our simulation work, or more specifically John and Mark's simulation work. But this last paper, a conceptual design for a new FoRest of scintillating tubes, is really the progenitor for my project. I'm building this conceptual design. I'm in fact actually the last or the only physicist doing experimental work for John right now. Brian Crow will hear about his project NewLat near the end of my presentation. And John wanted me to make sure to give a shout out to other people in his group, so that's why I'm going on my way to say this. So Brian will hear work on NewLat, but Brian's finishing his dissertation at this point. So I'm the only person in the labs, meaning I'm the lab supervisor, and I'll be supervising an undergrad this summer. And so if John is the ultimate PI, right, he's the principal investigator, right, then what would that make me? And I've decided that that would call me, oh, did I get, looks like you cannot hear me. No, I cannot hear Dr. Bindi. What that makes me is the penultimate investigator. So as penultimate investigator of the neutrino design, let's see. I had to break down this idea when giving this presentation on whether or not I wanted to give the audience a review of the physics of neutrinos first, including flavor oscillations, the mass spectrum, etc., or to go over the history. Now, I agree with probably what everyone's thinking. History is a little bit more boring, especially if we're going all the way back to the 1950s. And so, I promised that I've put pretty interesting pictures in between. So every 4 or 5 slides, I promise there'll be something visually nice for everyone to see. And I think this will be a good way. But at the end of my presentation, I would love to hear feedback if you guys would have liked this reversed. So first we have Rhines, who ends up actually being a large part of many of these experiments, but reactor neutrinos are the first types of neutrinos discovered. They validate a theory made, or antineutrino specifically validate a theory made by Dirac on antimatter for missing masses from the 1920s. So that was a pretty big breakthrough. And from this, we have accelerators which are able to add relativistic energy and momentum to particles, leading to different types of masses. And so we get, I'll go a little bit more into the standard model in a few slides, but muons are a little bit like heavy electrons. And so if electrons can produce electron neutrinos and then suddenly accelerators are producing muons, we're now finding muons are producing neutrinos and we have to call them something different. So this is what I would refer to as families of neutrinos are first discovered. Handedness comes from the idea that, and once again, I'll go over the standard model a little bit more, but that in all of our reactions, we want to conserve momentum, and that includes linear and angular momentum. In reactions, we want to have charge conservation, parity conservation, and like handed conservation, like angular momentum conservation. And having all 3 of these is often not possible, but handedness is a measurable quantity. It's also, depending on the type of particle, also referred to as helicity or chirality. And they're related concepts. And just at this point, this isn't even fleshed out yet in quantum field theory. So what's important here is just that we see there's a tendency, a statistical tendency for neutrinos. There's a measurable property of a way that their reactions always occur. So larger detectors are built in the Kolar goldfields of India and in South Africa. Cosmic rays and atmospheric neutrinos are detected. Atmospheric neutrinos coming from charged particles hitting the atmosphere, producing muon decay, muons producing muon neutrinos, et cetera, cosmic rays, atmospheric neutrinos. And finally, I don't know if we can see with that zoom bar in the way, but neutrino mixing and oscillation is theorized finally by Makai, Kagawa, and Sakata. So, what is a cosmic ray? Well, as those of you that saw my first talk, you know that I'm very interested in black holes and torsion, and when you have a massive active galactic nuclei and it's twisting and turning, it's producing vortices of supercharged magnetic fields. And these magnetic fields boost particles to relativistic energies, and these get accelerated due to these magnetic fields, such as a proton, and they get jettisoned towards Earth. A quasar that is facing towards Earth is known as a blazar. So this is an example of a blazar. What I want people to notice here is that we have the particle decay, just as you've seen with maybe bubble or cloud chamber experiments or at CERN. We have pions decaying into more elementary particles such as electrons, positrons. We have muons going on with more decays, and then finally we have neutrinos and gamma rays. And then the final part of this picture that I think is really illustrative is that gamma rays keep going and neutrinos keep going, but only neutrinos will appear as a signal on the far side of the Earth from a blazar. Obviously, gamma rays do not pass through the entire Earth. So this is really important, and at the very end of my talk, you'll hear me say that this line by John, which I thought was really poignant, that neutrinos are pretty much the only particle you get which knows its directionality as a signal, even as a scalar pickup field. So that's really cool. So back to the history of neutrino detection. So the Homestake mine becomes a huge deal. It's still Rhines, our first physicist from the 1950s. He's still at it at the Homestake mine, and finally solar neutrinos are discovered, right? But let's say that the sun, the solar neutrinos, and the cosmic neutrinos sometimes produce muons, right? We know this because they're higher energies. And we know that our reactor neutrinos, ones from maybe a uranium inverse beta decay process, almost never produce muons because there's not sufficient energy to produce muons. So if we're measuring the solar neutrinos, we should expect some rate of muons relative to some other types of neutrino signals. And what they find is actually there are missing neutrinos. This ends up being a huge issue and really revolutionizes the field and earns a couple of Nobel Prizes. In order to help figure out the missing neutrino problem, physicists want to maximize the amount of neutrinos detected from solar radiation. And this culminates in DuMont, which is a project centered in Hawaii. And the idea was to build a neutrino detector at equatorial waters. Water, because you can have a very, very, very large volume that's easy to suspend things by, and the water acts as a shielding agent to muons and other types of radiation. However, I will get into it in the next slide, but it doesn't work out. What's important though, and I really wanted to emphasize this because I'm giving this lecture for 712, and Dr. Bindi has emphasized that kind of the theme in this class should be introducing new students to the great experimental research that this university has done. And DuMont was really a UH idea, and the UH workshops are primarily responsible for designing the DuMont sensors. And so in the next couple of slides, what I'd like people to focus on is the similarity that DuMont has had and the influence it's had on a lot of projects going forward. And these are to name a few, which are all covered in the paper, so I wanted to put them here. I got to look up the paper and publications for each of these and read about them, which was quite fun. But basically the idea of DuMont was to have a large power and signal cable ran around 30 kilometers out. I should use the mouse, I suppose, instead of pointing at the screen. So around 30 kilometers out from the shore of Oahu would be an array of... I have
this as a pointer, so if you want to use this.
Oh, I meant because Dr. Bindi can't see where I'm pointing with the mouse.
Okay.
That's all. But everyone here can see the mouse. Yeah. But thank you. So this array of almost like pearls on a necklace. Each of these is a small central module, which I'll show you a better picture of the next slide. But just to give everyone an idea, this is almost 5 kilometers underwater, and it's deep in the ocean off of the shore of Oahu. And I guess the sensor is 50 centimeters. That's, I guess, an understandable size. We'll get into the idea behind detector mass. So whenever you see these detectors and their different sizes, one should consider that the bigger your detector, the more neutrinos can probably hit it.
So sensor module, how many of them you have there?
Oh, DuMont was never finished, so not even an applicable question, yeah. But DuMont versus IceCube. So DuMont is not finished. In 1995, there's a funding crisis and it's canceled. However, many years later, we have physicists from the University of Hawaii working in Arctic, the Antarctic, the South Pole, and we could really see that the design similarities between Dumont and Ice Cube. Where Ice Cube, the difference is that these are put in the snow or the ice of the South Pole. Oh, that shouldn't have happened. Great. So the idea of Dumont was, let's put it up here. The idea of Dumont was to have equatorial water-based neutrino detectors. And so Dumont with European characteristics is, well, hey, we have the Mediterranean. Why don't we put neutrino detectors in the Mediterranean? That's close to the equator. And so that's what we have. And we once again see this kind of design of this pearls on a string, and we have on the bottom the Dumont sensor original and the KM3net European design that is currently being built. So KM3net is in production right now. It is not fully developed. I believe the first phase has been deployed, but it is not fully operational nor doing data collection yet. But we can see this very, very, very similar design. And then similarly, we had the pleasure of hosting Dalian Xu, and she is a pretty big name in Chinese neutrino physics. She is leading a huge project. I believe it's somewhere between 10 and 50 square kilometers of the same idea of this deployed array. And she's doing it in the South China Sea. And this proposal, I'm including it just to emphasize there is a huge amount of the Chinese physics community ready to make this type of thing happen. And she has been instrumental in a lot of the neutrino projects here, and she's on a lot of international committees. So when I saw her talk, the question I had for her was, she was sharing my office, by the way, because my office is given to me by John. So of course his guests get to use it. So I'm getting to talk to her, and I asked, so a bunch of neutrino detectors that can detect nuclear reactions in the South China Sea. With that, would you ever be worried about nuclear submarines producing noise? And she gave the biggest smile and laughed, said, no, of course not. The calcium in the water prevents that. And I have yet to verify that claim, but she told me afterwards in private that I asked very smart, interesting questions, and she liked that.
So what kind of noise do you talk about that?
Oh, I was making a joke that if you're building 50 square kilometers of neutrino detectors, which specifically can detect nuclear reactions, and you line the South China Sea floor where the United States, if it were to get into war with China, would try to blockade, right, through that strait, that's how you would detect a nuclear submarine, is you just build nuclear detectors at the bottom, or radioactive detectors at the bottom of the seafloor.
So there's various ways that is you can detect the nuclear stuff.
Yes, of course. Acoustics being the best way. Of
So
course.
whenever you have the mechanical devices is running,
Yes.
you got a noise.
Yes.
So
It was only a joke I made to her. The point being is that this is a very, very serious area of development with hundreds and hundreds of millions of dollars being spent worldwide on neutrino detection. So we're going to go over some different types of detector design. The first will be the monolithic detector design. When I say monolithic, it means that the detectors are all put into one area and we consider it one single mass. So for example, at Daya Bay, there were 3 units for detectors, each unit being one of these. This is one unit. And then in each unit, we can see that there are 4 subunits. However, each of these units we would consider to be a detector, okay? So this is one total mass that we can consider at one site. And inside each of these, we have a hemispherical version of what we saw in Dumont, which is basically a scintillator being a chemical which glows when excited, a scintillator inside some container. Usually this is a liquid scintillator. Daya Bay ends up being really important because it shows that having 3 different detectors at different directions gives angular resolution. And one of the most important things here, the area of importance for our research, diabe, a lot of people's, is nuclear non-proliferation. So one would want ostensibly to be able to detect nuclear reactors, and so let's go through the different ways we could do that. An improvement on the diabe thing is Reno. Reno is the Republic of Korea's version of diabe, being the Japanese version of this. But I think Reno really improved on this by having a really awesome, unique thing where they have a bunch of nuclear reactors in a straight line. And then the detection setup was to have a detector 150 meters from some central point between two of the reactors, and then a order of magnitude higher or farther away detector. And this distance, I think, is great data, like physics collecting. The setup for this, I think, is awesome. And so one can see that we can pick up on angle, we can pick up on mixing, or I will get into it, but one should just start thinking about that as neutrinos travel, especially underground through dense material, masses, flavor, whatever that means yet, I'll get to it in the slides, but it changes. So this is great. Having the distance and the different angles is important. And in fact, Korean physicists have been instrumental in this, and so I thought this was so cool. There's this project that I'm doing, a lot of what I will be doing personally will not be discovering anything. There's not new physics for me to do, but I'm in charge of developing and designing a detector, which is a little bit engineering. If you were to ask me what new physics there is, specifically for me to detect, like out of my data, it will be this 5 MeV excess one day. Because reactor neutrinos, no matter where you look, always have this bump. And this bump is an unexplained problem. And Dr. Ju in 2016 pointed this out. So I really wanted to include this because Dr. Yoon is here, and so I wanted to give a shout out to the ROK and the amazing physics being done there, but also to emphasize that even if one can look at it as a detector design, one can also see that new physics is ready to spring up at almost any point. So this is really cool. There's an unexplained problem all of a sudden. So the monolithic design looks like this in some ways. So at diabe, we saw those 4 subunits. Each of these would kind of look like this. Camland has a great example. We are looking, by the way, these humans inside this shell are inside this chamber here, right? We can see that these are the PMTs, or the liquid scintillators, sorry, the scintillating tubes here are these here. And then these phototubes are at the bottom. And it will be really interesting. I want people to kind of just notice that we have a very large, what's considered to be a single mass for the scintillators, and then phototubes at the bottom. And by the time we get to FoRest, I want people to really notice that our design will have different placement of the phototubes, and geometry will be really important. So right now, this geometry maximizes only that it has a wide flux, right? Things are caught, but directionality is confined to only one dimension, which is signal. T2K is a bigger, more sensitive version of this in Japan. John is actually going to be flying out in a month and a half to go check this out. Super cool. Really beautiful photo. I promised everyone pretty pictures. Here's your pretty picture. What I want everyone to get from all of this as we transition now from the history to the physics of neutrinos is that these types of detectors from the 1950s has done 2 important things. Weak interaction is confirmed, and I'll go over what weak interaction is in a minute. But basically the W and Z bosons are confirmed in Q of T, and we are able to put limits on neutrino mass, but we aren't able to fix neutrino mass down, so then we can talk about neutrino stability. If we can't know the mass, then how stable is the mass? If the mass changes and is unstable, how many types? We're able to constrain that. We've gotten down to 3 or possibly 4. And then finally the energy spectrum, which, as I said, Dr. Ju pointed out that the 5 MeV spike in reactor neutrinos ends up being a brand new problem today to solve. So this is supposed to be a cute diagram. I will go over this again in detail, so don't worry too much, but it's meant to be a cartooned version of a Feynman diagram, as I will be showing a real one later, so I wanted to prep everyone. On the left, we have our inputs. In the middle, we have a cartoon of interaction, and on the right side, we have our outputs. It doesn't mean that they physically transferred over, it's just for illustrative purposes. So one of our inputs for inverse beta decay is the electron antineutrino, which needs a threshold energy of 1.8 or slightly above MeV. So if everyone remembers from their intro to quantum mechanics class, there is the square potential problem. One can imagine that the square potential is 1.8 MeV high. So this electron antineutrino needs to interact with a proton. This proton is provided by our scintillator's flower. This flower just being a proton-rich chemical. As these two have a scattering event, what is produced is a positron and a neutron. Let's first focus on the positron, and then we'll get into the neutron after. The positron will in the most likely case, immediately or very, very, very quickly, on the order of 1 nanosecond, collide with an electron. Of course, if you're nitpicking, there are other possibilities, but we're keeping it simple. And this electron-positron annihilation produces a gamma ray. This gamma ray will then be able to be detected in the phototubes of our detector for FoRest. And what is the energy of this detection? Well, the positron and the electron both have a relativistic mass energy of 511 keV, and we have that threshold energy of 108 or 1.8 MeV. This leaves a kinetic energy for the neutrino to deposit an energy for the photon. For everyone that hasn't taken particle physics, I would just like to emphasize that what we should really focus on here is that there's conservation of mass and energy going on. We have some energy coming in, we have some energy coming out, and we know the constraints. Because of that threshold energy and because of the rest mass energy of the electron positrons, we know the type of signal we should be getting out of our visible energy. So let's go into let's go into neutrino flavors. I've mentioned them a bit, and I think they deserve some discussion. So ostensibly, there are 3 flavors of neutrinos: electron neutrinos, muon neutrinos, tau neutrinos. There is hypothesized to be a sterile neutrino. I do not think personally it exists. We can discuss that at the end. But what's really happening, these 3 flavors, is that they're coming from what's called 3 generations of matter. And I will personally break this down just using electron, muon, and tau. Since we're not interested in the quarks, we're going to just ignore that. And instead, I will call the first generation the electron generation, the second generation being the muon, the last one being the tau. Of course, if there was a quark physicist, particle physicist in here, they would very likely call it the up, charm, and top generations. So just keep that in mind. What's important here is that anytime we have an electron having some interaction, right, where it's a particle or an anti-electron, otherwise known as a positron, whenever there's charge in weak interaction, the W boson is used, okay? Whenever there's electric charge being transferred or created or changed around with particle fields, W boson. Whenever we have momentum, and specifically angular momentum, right, we have the Z boson, which does not carry charge. It mediates transfer of momentum, spin, and energy. And it's that energy from the neutrinos that we saw on the last slide produces that visible energy. That's what's being conserved here. Is this Z boson is going from the proton electron antineutrino to the electron positron pair. So what does this look like? It looks like this. This is beta decay. This is a Feynman diagram of beta decay where time is going in the upwards direction, and we have a neutron spontaneously decaying to a proton and an antineutrino. In our experiments for inverse beta decay, we can use time symmetry to reverse this process. Instead, we go this way, down. So we would start with a proton and an electron antineutrino, and these combine to give us a neutron-electron pair. This is a footnote. If anyone has any questions about the actual QFT behind this, but the simplified version of what's going to happen is 3 neutrino masses. Given that 3 masses, and one can imagine this, I personally think of this as actually distance, like I imagine 3 vertices for a triangle, but you can use whatever you want for this analogy or the actual math. We have 3 masses. We know that each one is different by at least some amount. If all 3 are different, then 2 of them need to be closest together. All right, we'll call that delta 1, 2. The largest distance between the masses we can call S, 3. We don't know if the first neutrino, V1, or the second neutrino, V2, is the biggest difference. But we know one of the 2 has to make a big difference with the third one, because the other 2 are close. So the third mass difference has to be the difference between the 2, and we can just subtract out the deltas from each other. When practicing this talk, I realized it's too much effort to lift this thing up and write it, but one could consider taking out a piece of paper and doing this math themselves, and you will see that it comes out nicely. I guess I didn't say this explicitly, so I guess I want to say this. V1, V2, and V3 are like the 3 generations, because the electron, the muon, and the tau have these different masses and decay times. Great. Flavor mixing. How do we mix flavors? You don't just go to Ben & Jerry's and ask for 2 different scoops. You get 3 scoops, but you don't know what the 3 scoops are. You just know that the 3 scoops are somewhat different. How are they different? Well, there are 2 different ways I've talked about these neutrinos being different. We've talked about their masses being different. We've talked about their flavors being different. If we're going to build a basis out of the data that we have, that means that our 2 orthogonal sets of data will be the 3 flavors or the 3 masses. To transform between the 2 of these, we use a unitary matrix. I would like to point out that the Wikipedia uses star. However, if you're currently a physics student, you most definitely have seen this used as a dagger. It is not just the star. It's the complex conjugate transpose. So it's U dagger. But what's important here is that we have the Latin being the masses and the Greek indices being the flavors. And we can see that there's a matrix which swaps between the 2 of them. And what's interesting is that nature itself is doing something to swap between these 3. In terms of these, we're able to probe down to about 1% level. This will be kind of important when I go over the different detector designs and their efficiencies. So just a general idea of the types of experiments we saw earlier in terms of pictures. We have CamLand, right, and Diabase. So notice that Diabe, Nova, and T2K, these are not giving us information on the mass mixing. They're instead giving us the angular mixing. So what does that mean? Well, the masses are a basis, so the delta m's hopefully make sense at this point. And the sine squared thetas are the flavor mixing. So there's some angle of mixing between the different flavors and the masses, and detectors are not very good at detecting both. Or so far. Dun, dun, dun. So let's go over directionality, because this is a completely different set of thetas, and I just mentioned how detectors so far are bad at detecting both the flavor and the mass mixing, but we need to talk about actual thetas. So let's get into it. The basic idea of directionality is the ability to determine something from an incident direction, an incident being an incoming particle that ostensibly comes from some source, quote unquote. But that source is, in our case, is a nuclear reaction of inverse beta decay. Great, and I will start breaking this down more and more as the slides go. So first, we can note that from this incoming particle, we have this electron antineutrino, and I just will note. When I said our signal, right, my experiment will actually be using sodium-22, and it's a neutrino, I believe I'll be detecting, and then reactors use antineutrino. So if I accidentally, in the rest of this talk, flip between saying neutrino or antineutrino, my apologies. Because I want to get through some of this material rather quickly. But this neutrino comes in, and there's an inverse beta decay event. We have the positron fly off, get annihilated, and from there we're able to do a reconstruction. What does this reconstruction mean? Well, we can quantify this reconstruction's accuracy by angle psi, which is the difference between the true incoming neutrino vector and the reconstructed one. And that's basically the idea.
So let me ask one thing. So I cannot follow all of you. But what are you going to measure? What do you want to measure in here to verify neutrinos, which has the different mass and different flavor and whatever? What do you want to try to measure?
I am improving on the angular resolution.
Angular resolution?
Well, technically, I'm optimizing a two-parameter problem of mass and directionality, where directionality has been the poor point for monolithic detectors, the big ones. So I'm improving on the angular resolution.
Okay, so experimentally, how you can do it?
You'll see. I promise. I promise I will show it. So I will go through this. Let's see, how am I doing on time? Oh, yeah, okay. I've used about 50% of my time. 55, 60% of my time. Okay. I'll go through this a little bit quicker. Did everyone kind of get the basic idea when I first showed inverse beta decay? Mm-hmm. Okay, so some of these slides, as you can see, are screenshot directly from the paper because I used this slide deck, creating it as a way to teach myself the 3 papers I was put on. So if everyone feels rather comfortable with inverse beta decay at this point, I'll go through these a little bit quicker. And everyone loves someone that won't just read off the slides, right? So we have the positron receiving most of the antineutrino's kinetic energy, and the neutron takes a while to scatter. The key important thing is that inverse beta decay directionality is important to finding the neutron's displacement from its production at the inverse beta decay point. So this difference here is important for being able to produce fiducial data. So displacement from production is something that we can measure, and that's our reconstruction vector. This is a deeper overview of inverse beta decay in detail, similar to my slides, but I think everyone's okay with it. What's really important here is we can draw our vector from these 2 points. So I'd spoken about earlier how inverse beta decay occurs. There's the electron and the positron annihilation, and I said that there's a neutron that's also produced. This neutron is called a thermal neutron, meaning it's high kinetic energy and it's able to travel, and it's high enough energy that it can smash into a nucleus and get stuck. So it gets captured a while later, and this time difference between the two is what we use to reconstruct the incoming. And Zoom is hanging over this a little bit, but as Mark points out, and I believe this is from paper 2, over the simulations, but in paper 2, he points out that over time, and we're talking about 10,000 events, you're able to find very good truth with reconstruction. So, Dr. Yoon, I will start answering your question now. Diabay, we saw that quad unit, right, of those 4 cylinders inside that pool-looking thing. These are all kind of this shape. This one specifically is chooses. But what's important here is that we just have large monolithic detectors. They're able to be central volumes. You can build infrastructure and support around them, and therefore they can have a very large mass. As we saw from Camland's photo, we are talking about a 3-story building. These are going to be called monolithic detectors. Monolithic detectors have a huge disadvantage. They have no spatial resolution, which is important, especially when we're talking about stuff that's like nuclear non-proliferation. This is one of the reasons why Reno for the Republic of Korea was so important, because reactor neutrinos are important for nuclear non-proliferation and understanding what's happening inside a nuclear reactor for a non-trustworthy state actor, right? And so segmented detectors try to help solve this by having better spatial resolution, And the dependence for this is by overlapping Gaussian curves that we want to separate out. And the way that these are separated out is by having different cells get activated at different times. This is what NewLAD is, and I mentioned earlier that Brian Crow is writing out his PhD, and like I said, John made it clear. Shout out to Brian Crow for finishing his PhD. So yeah, thank you, John, for setting this up, and for Brian setting up NewLAD, because that leads to what my work is. And so, Dr. Yoon, you were talking about one of the things we want to measure, and we can see that this neutron, it can scatter from different points. So this neutron scattering twice, right, from the inverse beta decay event and then once more, it's very good clustering. But after 20 scattering events, this thermal neutron is very, very poorly confined. And so we're able, in a way, to think about this in a one-term parameter such as psi, and we really want to maximize this, this psi parameter, which results in, seeing this, a better, oh, and I guess this is important. It's a uniform beam of 10 keV neutrons undergoing scattering. So this is as if it was a reactor experiment. These simulations, by the way, if anyone's aware, is done by RatPack, which is CERN's simulation software. So the neutron scattering problem. So I just mentioned that this simulation was a beam of neutrons. Neutron scattering is the issue. So the challenge for any antineutrino detector is that the neutron scattering degrades directionality, as we just saw. Improving the position resolution is difficult, and in fact, actually, directional capability does not increase very well. What this translates to is you can build a bigger camland, and you're going to only have very, very, very small results. That's one of the reasons for Reno being such an intelligent detector design with those parallel nuclear reactors. But nowhere else in the world do you have that type of design usually for your nuclear reactors. So you need your detector to be flexible. So the neutron capture distance ends up being an issue. The Santa solution to the neutron scattering problem is that one should be able to segment and be able to find a tomography. Tomography, ask me at the end of the presentation what tomography means. It's a long answer, I feel like. But one tomography in a sentence is one would be able to reconstruct what's submedium or traveling of particles or radiation. So the loss of directional radiation, or the loss of directional information, is something that we want to improve upon, and you're able to do that with the segmentation. So you need the neutron to leave a target material and then come back in, right? So you need your inverse beta decay to occur in a proton-rich environment, right? You want your scintillating flower to be right there. You want it in high concentrations so you get good signals from the antineutrino. And then as soon as you have that inverse beta decay, you would really like that scintillating fluid to not be there. You would like to be in a vacuum, and you would like your neutron to just be able to fly away for some distance. Because remember, as the neutron travels away, we have a very, very, very strong relativistic limit on the neutron's velocity and kinetic energy. And so having that time delay allows us to be able to measure the kinetic energy of the neutron and get that signal for the reconstruction. So as shown in this figure, Santa proposes to do this by having a very thin target material and then a capture material that is thicker. And this is very, one would say impractical. There's major engineering challenges to be overcome by this. It is a unique design idea, and one of the only ways it's been come up with is that one can separate these into planes. One can immediately guess that if you're going from a volume detector to a plane detector, that maybe there's a trade-off we're about to start seeing with the Santa design, though. The Santa collaboration doesn't do a good job of having these large masses, and without these large masses, we still have these solar neutrinos, and we still have these cosmic neutrinos, we still have muon. We have all these issues going on with our detectors that really is only solved by having a big enough detector that we can scale up the noise. So Santa is able to get directionality and be able to fix these things with this neutron capture, but fails horribly with the noise. So a hybrid theory is needed. And a much larger surface to area volume exposes the detector to severe levels of background noise, Santa. But then the smaller target volume of Santa, on the other hand, restricts the achievable target mass. So in both cases, we have an issue because we want very low background noise in a targeted near surface deployment scenario. This is a technical speak for put right next to a nuclear reactor versus put farther away. Remember Reno, where we saw one 150 meters and one 1,500 meters, right? We would like our detectors to not be too badly messed up by that order of magnitude. The noise shouldn't be that bad as a difference between. The signal might change in intensity, but we wouldn't want noise to be different, right? But if our detectors are highly, highly susceptible to noise, then yeah, putting them in different geographic locations where just vibrations cause scintillations by trucks driving past you, it's an issue. On the other hand, if you don't do that, then you have practically small amounts of data for actual deployable environments in the real world. So Santa is also not practical. So we strike a balance, or Mark and John a couple of years ago went to strike out a balance, and they did it. And I see Ethan's loving all these background pictures. And so this balance, by the way, and this is cute. The reason why Ethan's smiling is I have been showing album covers where the first one's a joke. This is just called Hybrid Theory, but this is a mix-up between a rock band and the famous rapper Jay-Z. So it's literally a mix-up of two completely different genres. And so this is kind of this cute idea where you could somehow optimize the difference between these two detectors and the hybrid. So the idea between FoRest is that you want to maximize the neutron's free flight space, but you also want to be able to have high detector volume and mass, specifically mass. It can't just be volume, you actually have to have physically detectors in there that are doing it. You can't just have it spaced out in a large area. So the progenitor to FoRest is sand, segmented antineutrino, and NULAT. Once again, shout out to Brian Crow. And this kind of looks a little bit like this, where we have a segmented checkerboard design. One can imagine it being incredibly tall. And this is what was actually used in our simulations. Because we're doing simulations, we were not limited by engineering practicalities, and so this is a three-dimensional segmented detector design in a checkerboard pattern. Now one could easily see why you would use Dumont or all the other underwater neutrino detectors. How would you be able to host these unless they were very near weightless and you're holding them from a string, right? These are floating in space. However, these are incredible at detecting. So inverse beta decay events were measured out to 10,000. They're all compared. And I would like to actually go to the next slide. This, I think, Dr. Yoon, starts to begin to answer your question. So we can see that Diabay and Reno have absolutely almost no directionality. They're able to have a constraint on kind of a general area, but no reconstruction. NULAT, the original segmented design, has some, but very poor, and it's basically guesswork. Santa is perfect for this. But this is simulation data, and Santa doesn't work with noise. And Santa is very expensive because you have to have these very thin sheets of scintillators. Nonetheless, these are the simulation results, and I love this table because this is the table that put me as an author on 3 papers. This was a screenshot in Mark's PhD in the rough draft of the first paper, and I saw that. I was like, hey, you want me to hard code that just into LaTeX as a table? And that was the spark that led to me being on this paper. So I couldn't have done it without this table. What's really important here is that we have. Did you say something? No? Okay. What's important here is that we have different types of dopants. My project FoRest will be using the lithium dopant, highly segmented versus non-highly segmented. So we have the monolithic detectors versus what we saw at Santa, where it's very spaced, and NULAT, where it's thinly spaced. And then moving detector versus not, and mass tons. So as we can see, the masses being very small versus larger neutrino detectors. Great. There are only two important things to look at on this slide. My head has to get out of the way so everyone can see it in real life. These two green arrows. Dr. Yoon, this is finally your data results for what you were asking for. 3D checkerboard and 2D checkerboard are the simulation prototype or the simulation models for FoRest before FoRest ever had a name, and they were just looking at the possibility of this design being used. And we have incredible by an order of magnitude angular resolution, very comparable to Santa. As we saw, Santa was on the money, but we're improving by an order of magnitude while still maintaining volume, masses, etc. So we're getting good results for everything else. One way to look at this is number of counts detected. So choose is that big monolithic detector that focuses on just getting the most amount of counts. They're really good for cosmic and solar neutrinos along with reactor neutrinos. Highest number of counts. This is out of 10,000. You have a half detection by NULAT, less than half detection by NULAT, half detection by three-dimensional FoRest, and Santa is terrible. Santa has a 20% detection rate. Great.
Can you back there, that table? Can you explain about that is the table? This 3D and 2D and then experimental material in each time?
Yes, so the 2D and 3D is, this is the prototype of FoRest, so this is 2D, yeah, I think this is 2D, and this is 3D. And then these are the other ones, so non-2D. Everything that's not 2D or 3D is one of these three, where this is Santa. Santa's the only one that looks like this.
Okay, and also the second one was? It's back to, yes, in here.
Yes.
And second
graph
shows what? I can't see.
The second graph.
Yeah.
The second graph
X-axis and y-axis to show what?
Yeah, so that's just the number of counts. I'm so sorry, that is very, very small. And it says entries. So it's just the
Number
spread.
of events?
No, okay. So there is a spread on where the source comes from. So the way Mark does these simulations is that the angle.
Let me ask one thing, is this way. When the source is coming from the one direction,
Yes.
but it's almost like omnidirectionally they are coming?
No, so yes, that's perfect. The way the simulation works is you take the
That
source.
simulation is really, if we have to
Oh,
measure with them,
for a real detector? Well,
Yeah.
well, for a nuclear reactor, of course, the source doesn't move.
I mean, simulation, you can make that is all the sources as a direct, with a certain direction. But it's really, they all coming from the universe as omnidirectionally or so. Even you just have your sensors like this or that, doesn't matter with the same amount of coming. Or because of the receiving sensitivity of that, your devices, which you can have in here, you may have the different responsible. I mean,
Yes.
Yeah, because the sensitivity were all different.
Yes.
Uh,
So the way you do it is you test by moving the source in an arc around, and you test the different angles that work. So for example, Santa, if you're at 180 degrees to Santa, it detects nothing, right? So you want to make it a 180 degree arc around it, and so you do the same type of thing in 360 for all of them, or I think.
So is that the result which is Santa? On that, the one has, even after you make that is a 360 degree rotating and then?
No, this is, I believe, for one specific. So these are different graphs. So this, I believe, is for a beam source in one direction.
Mm-hmm.
This is, if I recounted correctly, this is the confidence that it knew some direction correctly. So remember how there's a reconstruction, and then we said over a number of events we reconstructed, and the reconstruction versus the truth has some amount. So if we can do multiple truths. We can do a truth from such and such direction, and this is the ability of the detector to get it right for a specific one, given one direction. But this is done over multiple angles, so you're completely right. And actually, Dr. you make a good point that some of these detectors would be used for reactor detection, but the Department of Defense and Homeland Security would be really interested in making it detectable for a moving source. And being able to cancel out the noise is really important there. And I promise, actually, okay, yeah, I definitely need to run up on time. I promise my slides will get to, I actually will incorporate a moving source for directionality purposes in my design. So I promise that FoRest will answer these questions. Yeah, so what's just important here is that Mark stumbles upon this thing that we see this great proof of concept for angular resolution. So we have two constraints, right? There's a 2-parameter problem, and we want to have the thickness of the proton-rich scattering medium increase the average distance, but we also want to have a separation with a large target mass. So if you have a large separation, then you've lowered the density. Since the separation is a vacuum, right? We do not want, remember that from that slide where we had the 2 scatterings versus the 20 scatterings? We saw the 20 scatterings was bad. So we want very low density for the neutron while it travels, but we want very, very large target masses for our detectors in the first place. These are conflicting requirements. So we propose FoRest. We help solve this problem by a couple of unique engineering solutions. Instead of using plastic, which everyone has been using since Dumont, we use quartz, and specifically high purity synthetic quartz with incredibly low radiation background count and incredibly high optical transmission. Inside this is a pure liquid scintillator that has been the same one used in CamLand, so I specifically ordered the same exact chemicals and followed their publications for how to develop their exact thing. So we have a matching type of scintillator which should produce the same types of signals. Plastic tubes would be more cost effective, but if everyone remembers, plastic is a hydrocarbon, and hydrocarbons are proton rich. Oh, our design is a FoRest. So FoRest stands for a FoRest of scintillating tubes. We have a vertical scintillator filled tube. We have photomultiplier tubes or silicon photomultipliers at either end, and flexibility in the dopant in all or some tubes. And let me, because of time, I will point this out as we go. But I will keep bringing these 3 up. These are incredibly different design choices that seem small on this slide, but are a big deal. So this is kind of what it would look like. It's huge in some ways, but if we remember what Diabé looked like, if we remember what CamLand looks like, where we have people inside a thing that looks like a 3-story building that's the size of a nuclear reactor housing site with major amounts of concrete, this is actually small and very low maintenance. This is much smaller infrastructure overhead. You also, by the way, one huge improvement that needs to be emphasized, and I will keep pointing this out, we saw that checkerboard design, right? How were we able to do that? You do it by just not filling some of the tubes. This modular design process. Now it's possible to record the time and location of the neutron's first scatter after exiting the tube where the inverse beta decay event occurred. And then the neutron's able to travel through multiple tubes and then we're able to capture it a while later and be able to reconstruct the kinematics. The way we're able to do this is a huge jump in technology. This is the most expensive thing I've ever purchased in my life. This is an over $10,000 digitizer. Specifically, this digitizer can do 2 important things. 1, I must emphasize that as opposed to other setups that did not have PMTs at both ends, but instead only at the bottom of their designs, our design for FoRest has detectors at both ends. And if you have multiple tubes, each detector has 2 photomultiplier tubes on each end. So if you have the inverse beta decay event, and then later you also have the neutron capture event, both of these signals need to go to the same digitizer. The inverse beta decay event occurs on the nanosecond scale, and so we bought something with a resolution at the nanosecond scale. And the final other thing is this pulse height analysis. By having a very, very clear, constraint on the relativistic energies expected from these neutrinos, and I will jump the gun a bit and just tell every physicist in the room, we're using sodium-22 as our test, so we're very sure on the relativistic energy signatures we're expecting, right? And knowing that, we can do pulse height analysis to cancel out noise, do a very fine constraint on the efficiency of this. We're gonna have a dual gauge discriminator. We spent another $1,000 in software, so that's very cool. I get to learn all that. And I also got to do a little bit of engineering. So this was me learning about the radiopurity of quartz. If those of you who haven't done experimental research yet, you will eventually know the name NIST. NIST is the National Institute of Standards and Technology, and they're the good guys that help out physicists and engineers for free, figuring out reference tables for materials. And it turns out that we would all really like, if we're all scintillating neutrino detecting physicists, we would really like to use Hirsys supersil quartz or something similar, where we have incredibly low amounts of uranium, thorium, and potassium. This is what it looks like. So Dr. Ethan, both of you heard me give a talk on theoretical physics last time, and me talk about how I'm interested in computation and theory. This is what it's like being an experimental physicist. And if I was giving this talk to first year graduate students, I'd point this out. I would like to say that this email chain started in, October 12th and goes from November 1st all the way down into January. The result of this email chain produces these almost $700 synthetic fused silica quartz tubes. Let's get into what these look like. I like it. I saw Ethan's eyebrows raised. This was a great slide to put on. What was this like for me? Well, what does this $700 thing look like? We're looking for something like this cuvette, but a path length of 1. That's how this email started. So when I was tasked by John to make FoRest, right? Now everyone knows what FoRest, raise your hand if you kind of understand what FoRest is, right? It's a bunch of tubes, and these are better than a monolithic detector. And I have to build the tubes myself, make the scintillator, put the tubes together, build the detector. And so I have to purchase the tube. And it starts with this line. We're looking for something like this cuvette with a path length of 1. And this whole mess that took me 4 months in the middle of TAing and everything. You wanna know what that looked like? I saw this on a website and I just asked them for a custom version. That's being an experimental physicist. And so doing that turns into this. This is my first diagram for FoRest. This will be the tabletop experimental version that I'm doing, and we'll see in a couple of slides the version of that we expect to be carried out in 5 years. But this is what I'm actually doing in 109, and anyone here in the talk, you're more than welcome to come say hi to me, and I will show you my experiment. The idea is that we have a PMT on either end of our photomultiplier tube. I'm so sorry. The PMT is a photomultiplier tube. We see it as these blue caps. Inside the quartz is a scintillator fluid that I filled with green, because who doesn't think of green when things glow? And the scintillator fluid has a source pass between them. Unlike Reno, where we have those large distances, there is no nuclear reactor on Hawaii. So I'm going to take sodium-22, place it on a stepper motor between these 2 tubes, and I'm going to run the sodium-22 with the stepper motor across the length of these tubes. Sodium-22 is going to decay, leaving antineutrinos. They're going to produce the inverse beta decay event, or the beta decay event. The inverse beta decay event produces the electron-positron pair, which produces a gamma or a gamma ray, and this hits the PMT. That's our first signal. This occurs at the nanosecond scale. At some time later, the neutron, which is knocked free, travels into another tube, which produces a signal, which also hits the PMTs. Note that we are finally getting directionality by two choices here. It is not just having the two tubes, but having these different PMTs, because as the source moves from one end of the PMT to the other, we get what is perhaps maybe not because of velocities, but similar to like a Doppler effect, where we are able to see the distance between these two events given our two detectors on either end. And that's very new. So the final design for FoRest, what it will eventually be, is planned to be in Ohio. The Perry reactor was just approved to stay online for like another 5-10 years. The Far Park mine, everyone's heard of Morton Salt, right? It has the girl with the salt hanging out. It's a blue cylinder. Morton Salt was mined out of the Fairport mine. And so the idea is to put the FoRest inside the Fairport mine where it's shielded from solar neutrinos, muons, etc. And we will get a clean signal from the Perry reactor. So one of the diagrams for this would look like this. I've tried to show that the reactor will send antineutrinos. It will pass through some of these detectors at some point. It will hit one of the tubes. In this design, I've shown the segmented application where the segmentation allows the neutron to go through. Remember how we want to reduce the scattering for the neutron? As the neutron goes through the quartz, it may or may not produce a scattering event, which itself, because of the PMTs, can get possibly a sign. It would be a very low signal. We don't expect much, right? Because there's no scintillator fluid in there. But this is one of the constraints we can put on. And then finally, we should get a bigger signal again. So this coincidence timing is around the 10 nanosecond scale, which is well within our digitizer range. And if we space these out more, it's better. Finally, muons are not getting into our design. And then a slightly cluttered version of what this may look like is on the right. These are actual pictures of the Perry nuclear reactor and the actual core of the Perry nuclear reactor that I found online. So credits to them. This is actually the Perry mine. And so once again, we have this idea of muons getting blocked by the rock and reactor neutrinos coming in and producing events. Oh, and I include this. I tried really hard late at night to get these to semi to scale so everyone can see that it's not quite right because it looks a little funny because these tubes are smaller relative to the construction vehicle and these humans are next to bigger tubes, but both of these are relatively to scale for a 10-meter tall detector. Keep in mind, once again, this is relative because we wanted to have that mass problem, right? We're using Santa's segmented idea to be able to get this directionality finally, but we're playing against we're comparing ourselves against detectors that are 1 ton in mass, and they're 3-story buildings. So this is relatively small and modular. That's what makes this a breakthrough detector design. What does that look like right now? This is from where it started. This was an experiment before mine, and then we built it up, and I have placed a stepper motor between the two, and so we can see that we have a base with nice separability. And it was really interesting. I had 0 experience with optic bench material, and I now know how to use optic bench material. So this to bring it all around to full circle, I'll wrap it up in 4 minutes. Bring it around full circle. In my last talk a few weeks ago, I talked about torsion. Its effects on mass. Does everyone remember that? The more massive an object is, its quantum spin is coupled to the relativistic twisting of space-time of a particle. I've talked about flavor and mass mixing, right? For the neutrinos. I've talked about how the muon and the tau neutrinos come from heavier generations of matter than the lighter electron generation of matter. Well, it turns out there's an unsolved problem in the standard model. A really big problem that's been around for like 15, 20 years. And it's called the analogous magnetic moment of the muon. And there's a really cool idea between the connection between this and flavor mixing, which is also unconstrained. And the idea is this, is that it totally makes sense that if you talk about spin torsion coupling, and neutrinos are known to do higher amounts of flavor mixing through denser material, of course it makes sense that higher concentrations of matter should have some effect, since the neutrino is a gravitationally coupled particle and it's not charge coupled. We saw that, right? The neutrino deals with the Z boson, it never deals with the W bosons with charge. The neutrino doesn't care about charge. So how could neutrinos interact and change flavor? There are many theories about neutrino flavor mixing causes, mechanisms, but a beautiful one would just be, well, yeah, you're going near dense matter, and dense matter couples with you. And of course, if you're basing that off of spin, which is the neutrino, neutrinos are just the conservation of a nuclear reaction's energy, angular momentum, and directionality. So this is really beautiful and really cool. So this goes back to that first paper I showed, and you can actually solve the anomalous moment of the muon by having this coupling term. I threw this in because this is really funny. So if you ever get a chance to look at that first paper, sometimes physics is not very good. And this is what I wrote in a white paper of mine, that sometimes not having data and self-referencing is not always the best call. Here we had an amazing claim. Something in the standard model that's unsolved is easily explainable by our math. We just introduce a new term, L. But as I point out, all too many problems in physics, right? This is supposed to be a talk to incoming graduate students. As someone that's had a couple of publications and looked at issues in physics, I think a big issue is reproducibility. And I've mentioned a couple of times that what is the physics I'm really studying here? What are the new discoveries? There's a 5 MeV bump, but Max, what are you doing? And I've been pretty honest. I'm doing engineering. I'm building a detector. But going beyond back of the napkin estimations, collecting the data, trying to improve on detector designs is worth it. I appreciate everyone coming to my talk. In summary, I will just say that I have shown how a small and exciting hypothetical inverse beta decay detector has now ballooned into an actual project that is paying for me to exist in Hawaii, which I'm very thankful to John Learned for. Given a sufficient number of events, we're actually able to make this into a detector that will revolutionize the ability for physicists to have directionality along with mass. It's modular, so meaning these projects should be cheaper because you can build only so many scintillators as opposed to one large one or 3 large ones as we saw at Dana Bay. At these distances, such as maybe 10 meters away from the reactor, we can also study the source distribution of neutrinos being produced in the reactor core. So one could imagine placing these rods in a circle around the reactor, 10 meters away or 150 meters away like we saw at Dana Bay or at Reno. And a different set of frost appendages like at the salt mine, which I was showing underground. Modularizing these, but having the similar design produces a coherent judicial model. And that is unrivaled and does not exist currently in the space of neutrino detectors. Why is this worth it? And I think, I really like this. John is known for his quips, and I thought this was a great one. While not an easy task, it is a remarkable capability unique to neutrinos, the only stable elementary particles which know their point of origin. And so having directionality and maximizing directionality at the cost of slight mass detection amounts, and as we saw, I mean, we're doing great. It's able to detect things at a comparable rate of around 80-something%, I think, to the mass detectors, the massive monolithic ones. And I'm excited to be a part of this, and I appreciate everyone coming and listening. So, acknowledgements. Yeah, everything came from Mark Duvall's paper. And like I said, this was my chance to really learn about his publications and work. And justifying being an author on them. I want to thank John Learned, and finally thank you to you guys. This was a very long talk, and it was very scattered. And if you have a sense of humor, yeah, Ethan, I love it. Yeah, Dr. Eden, yeah. If it's a very scattered talk, you get bad results. I thought that was a great joke.
Okay.
Yeah.
Next one thing is that is, can you back to that the digitizer, the which you say that is a very expensive one? Yeah. What is the reason why you try to use this digitizer for your experiment?
So you saw the PMTs at the either end of the tube, right?
Mm-hmm.
So if we didn't have two PMTs, then we would only get one signal. We would be able to pick up the inverse beta decay event.
Yeah, but digitizer, you just, after you receive the data,
Yes.
and then you just digitizing that. What's the reason why, without any this kind of digitizer, what's the difference between before, without any digitizer, you cannot do anything? Or-
They're too close of events. Also, well, how would you do it? So so imagine this. So instead of a multi-channel digitizer, let's say each PMT had its own digitizer. So there's 4 digitizers now instead of 1. We have our, let's go to, thank goodness for the slide. Wait, where did I put it? I want to get to my,
So actually, even one PMT,
there we go.
so one digitizer,
Yeah.
so that digitizer gonna do what? With
Yeah,
that
perfect.
signal? Yeah.
So let's say we have only one digitizer at, let's call it the northeast quadrant, right? The northeast digitizer is able to pick up the signal from the neutrino, right?
Mhm.
We're able to pick up the energy.
But
Yeah.
that digitizer didn't pick up the signal. That is just,
from the PMT.
yeah, the
From the-
PMT already.
Sure.
And then you just try to numbering them as the one of the signal.
Yeah.
So I don't know,
Yeah.
what does that mean? If you, without any digitizing, all mixing get together, then what's gonna be the difference between them?
Well, imagine that I have these tubes sitting in 109 Watanabe with no source. Then one would expect cosmic and solar muons to crash through the ceiling, right? And occasionally cosmic neutrinos to crash through the ceiling. And those, along with the radioactive isotopes in the room, would set off these things at some background, right? And I'm not quite sure what you mean by before the digitization, because how do I know it's on?
Yeah, we have no idea about that.
Yeah, I
where
need-
that is
yeah.
so coming.
Yeah.
And then we have some sensors
Yeah.
using the PMT, in that this will get us some signal.
Yes.
We're not sure where it's coming from, is what kind of event they have, but if something happened, and then we have some signal, one. Another signal from other, and then the many kind of difference, the detection as you have.
Yeah.
Now, why you wanna limit with that is digitizer. Digitizer has a certain limit, rather than have tried to.
Because we need the coincidence. Because this source, right? I'm going to collect the data on moving the source, right? It's on the stepper motor.
Mhm.
So if the source is, like, this picture is kind of a little bit bad in some sense. I can actually probably do this. I'm glad I made these slides like this. This, let's say I'm moving the source, okay? So if I take the source and I were to move it over here,
Mhm.
oh, I thought that arrow was going to stick to it. Let's get that arrow to stick to the thing. Great. So as I move the source around, let's put it here. Oh, it didn't move. Okay, well that's fine. If the source is there, let's have the arrow go here. Well,
Mhm.
if it does that, then the PMT over here gets the signal first, and we should get a 1 nanosecond delay. If the timestamps are accurate on whatever the recording device is, let's say we're in the 1950s and we don't have a digitizer, whatever shows the timing, the timestamps, there may be a difference between these two. But unless we have a digitizer at like this gigahertz frequency thing, no one has the ability to detect the difference between these two PMTs. But would you a 10 nanosecond difference or smaller, right? These are incredibly small events. I mean, actually, no. This is. I need to do the math.
Simply the reason why, because that is you need the time synchronization.
Yes, time synchronization. And there's two levels of time synchronization, to be very clear. The two tubes allow time synchronization between the IBD event and the neutron capture, which is Mark's research showing that given 10,000 events, which is very reasonable, 10,000 events gives you this very, very good signal and directionality, signal to noise ratio with directionality.
So actually that 10,000 event occur at a different time.
Mm-hmm.
And then you just want to try to set as the one starting point and then try to see all together, as that is the reason why you need the time synchronization of that?
No.
The data collecting that?
Let me see if I understand. So,
I don't know. I have no idea that, but there's a lot of particles is coming in.
yes.
We have sensors like that,
Mm-hmm.
and then which has, let's say, the same sensors we have. If that is just one event,
Mm-hmm.
and then even we have to measure it different way, but we want to try to set as the starting point, as the time synchronization, and then to try to see. Is that important? Or, I mean, using such a digitizer,
Mm-hmm.
that's simply some analog signals or whatever,
Mm-hmm.
they try to collect and then transfer that as the number.
Yeah. Yes, so okay, so the reason why it's important is that we're going to get 4 different numbers, each with a real timestamp. And physics does, like the universe provides enough information to us that these are 4 different times, right? The universe knows that they're 4 different times. The digitizer is necessary we need one unified master over 4 slave signals to always have the correct order of those time signals. If they were all different, then there could be a delay because of the wiring, right?
Yeah.
But by having one digitizer that is good at the nanosecond scale, it's hoped that these two PMTs can also be calibrated with this difference. So this difference, I could fix this without the digitizer by just making them farther apart. Like if I just literally move these, they're currently in 109, I have them spaced 6 inches from each other. Because we wanted around 10 centimeters, which gives you 10 nanoseconds. And our digitizer was like 10 to 5 nanoseconds, so it's like, okay, good. But if you wanted me to, I could move them 60 inches apart, and then I would 10 times
Yeah,
the
so
amount of
as relatively, as long as you know that is spacing between the sensors.
Yes,
So you already know.
yes.
So not necessarily you have to digitizing and then the letting has synchronizing with this, because you already got that information, which.
But that'd be by moving it, right? To have it be accurate at this close setup that we have and have all 4 consistently be a fiducial signal. So we have 2 different sources of confirming our data, right? We have the first event and the second event, keeping in mind that this thing is going to continually go off. So this tube should also be having signals that get sent to this. So there's going to be a lot of background data, and these PMTs are going to be firing off almost continuously, right?
Yeah, I'm just curious, but why we need to use that that's the reason why I'm asking you.
Yeah, it's for coincident timing. Coincident timing between the 2 tubes, and then again for the 2 PMTs at either the caps. The resolution is important for.
Yeah, for the spatial resolution or the temporal resolution.
Yeah.
Because of that, that's the reason. But as we already knew,
Yeah.
such a kind of a resolutions, then we can choose the right digitizer, but if not, I'm not sure that's gonna be necessary to.
I will be honest, I did not purchase the digitizer, I did technically purchase the digitizer. It is true that technically spent $10,000 out of the budget. But, no, this was John. I contacted the company.
Some reason why.
Yeah, John, but yeah, it's the tubes, it's coincident timing, that's the general thing. Specifically, he really, really liked multi-channel, because we could have gotten a slightly faster digitizer, but then it would have been like single channel or something. It was weird. It wasn't gonna combine all the PMTs to one master unit. And all the PMTs going to one analog box, I think, was one of the things that was important. We have SIPMs. Oh, so along with these, right? Gary Varner has these SIPMs, right? And these connected to their own things that have their own proprietary way of looking at it. John was like, you have to set them up, and no one's here to teach you how to hook these. So we're gonna buy this thing. It's going to work. There's customer support. There's code. There's software. It's fine. And that's fine. So there is a cheaper way. You're right.
Yeah, it might be a little different aspects, but it's when you try to listen to some music, there's if we can someone perform in front of me, that would be great. But it's not, then we need a kind of a recording. So there's a long play, the disc, and also the CD, which is convert. Many of the old recording was converted as a digitizer.
Yeah.
And so actually that, we cannot hear it. So,
Yeah, I wish I.
yeah, just unplug it.
No, yeah, you're right. Here, Dr. Bendy, we should be able to hear you now.
Can you hear me?
Yep.
Yeah.
Okay, good. I felt like I was muted. Okay, good.
Turn on the.
I don't know why before yet. I was trying sometimes to interact with you, but yeah.
Oh, I'm sorry.
So I will need to go soon. I just wanted to tell you that you gave a very comprehensive talk. I really liked it. I liked the way you presented it, because you are very you have somehow a gift, right? Not everybody can present these things in a very natural way.
Oh, thank you.
And so I really like that. And you made these things very interesting too. Now I wanted to hear probably a bit more about your project, but of course for time, because you start from the history and everything, then of course this part was a bit more fast.
Yeah.
And plus, I don't know, when did you start with this thing? To work on this thing?
August was when John agreed, and I started getting paid January 1st, or January 5th, yeah, so I just started.
Yeah, you just started, so yeah, I don't want to ask you nasty questions.
Thank you, you're so sweet, I appreciate it.
That you just started to navigate and to get familiar with, and yeah, it's a great thing, the fact that you can actually understand better the directionality. I do not understand for the reactor how this is critical in the reality. While the directionality for certain other things is so crucial, because you want to understand if it's coming from the sun, if it's coming from a different type of source. But from a very naive question, but from the reactor, aren't you expecting to see them all from the same direction?
Yeah, so I know from a poster from Daya Bay, I believe it's in this building, and if not, the IFA definitely has this poster up. But you can see that in Daya Bay they have those 3 units, right? Those 3 setups. And one of their whole points was that you could constrain where a radiological source would be. And I believe their model or their simulation, their scenario was someone has a nuclear dirty bomb in a port, then place the reactor as the model idea, and they were able to use diabase setup, those three, and then I remember seeing on the poster that they only had two, and then they only had one, and you can see this rainbow gradient of uncertainty, and you can see that it's huge, and it's only constrained in one direction, almost like how aerodynamics look like with wind. It looks almost windswept from one direction with high uncertainty everywhere else, but as soon as you have three, you're able to triangulate. So having the modularized detectors that aren't, the size of a 3-story building, it's just a long tube that's relatively, high, it's quartz and scintillating fluid is not a delicate thing. You can place them just anywhere, inside a shipping container on the other end of a park or whatever. So that's why, but you're completely right. For a stationary reactor, it doesn't matter. But John will tell you that the Department of Defense would love for this to be able to work with nuclear submarines. he keeps saying it doesn't work.
Yeah, no, and plus I can understand you get more familiar with these technologies and everything, and then once you measure with a very high accuracy, it's like having a known source in one direction, exactly in one direction, and so you can really calibrate your instrument very well, and afterwards, if you use the same technologies to, as you were saying, in the ports or in the military bases or wherever you want to, in the airports, wherever you want to put these type of things, then with the triangulation, you are able to really understand where the signal is coming from. And the 10 nanoseconds, so these 10 nanoseconds are related to the distance or where you want to put those, right? It's centered in that distance, I guess, because you could go also to lower resolutions of picoseconds or things like this, but probably there's no need, because if you put them enough far apart, you get this signal with 10 nanoseconds delay, so you are able, I don't know, I'm just guessing, so it's enough, 10 nanoseconds resolution basically. Because in our case we have PMTs and scintillators, but we need picoseconds resolution, because they are very, spatially very nearby. So I don't know, it's more a question for you also for the future. I don't know if this 10 nanoseconds, where they're coming from.
Thank you for not asking me the hard questions. I certainly don't know.
So we leave it there for the future.
Thank you. Okay, well, I'll let everyone go.
But overall, great job.
Thank you.
Great job. Okay, I need to go now.
Okay.
And I'll see you in person. So not next week. Next week is spring break, right?
Yes.
But we do have a class. Am I correct? Also during spring break or not?
No, we're not.
I never go.
No. Dr. Yoon has the schedule up. No.
So we're not gonna have that. It's the next week after the spring week, and Ethan will give a talk.
Okay. Perfect. Awesome. Thank you so much. Bye
Okay. Bye.
Ciao.
Bye.
Okay. Good.
See what she said? So you should hear this. I did not actually know this because I slept in today. I knew I